The previous tutorials mainly considered training models with AutoML. In this tutorial, we'll consider doing inference in these models, that is, using the trained predictor to make predictions on new data. In this tutorial, we'll study key considerations in inference and deployment of such models, how to produce predictions in less time, and perhaps we might want to understand our trained predictor via feature importance. Finally, we'll conclude with some practical tips for autoglon deployment. First, let's produce such a predictor, and here we'll utilize stacking and bagging to boost its accuracy. Again, we're just working with the same diabetes data as before. Here we specify autostack equals true to produce a stack ensemble of bagged models, and then we load the same test data as before, and finally evaluate our predictions. And again, we're working with a small subsample of data throughout this tutorial. We encourage you to work with larger subsets to get a more realistic sense of how things work, but we just want to make sure everything runs quickly for you. And so we go through the whole stacking process that we previously described, and then we finally can evaluate the resulting predictor on the test data, and we obtain these accuracies and other various metrics. The previous metrics corresponded to predictions produced by the model that autoglon believes is the most accurate from its held out data. Recall that we can also evaluate the performance of every model that autoglon trained by the leaderboard function here applied to the test data. This produces the following results, where we can see that the stacker models and the output of the last weighted ensemble of the topmost stack layer tend to be pretty good on the test data. We can also see here the time taken for producing predictions from each model on the test data, as well as the time for producing predictions on the validation data for each model. Different models vary greatly in their accuracy and time required to compute predictions, or inference latency, we might call this. Low latency inference may be important for ML deployed in real-time settings where we have to make decisions quickly, maybe one data point at a time. Low memory footprint might be important for ML deployed on edge devices where memory constraints are severe. Overall inference costs might be important for ML deployed in cloud settings where we don't want to pay too much money for a model that is of limited commercial value. So we can see that we have various considerations here that may govern which model we actually think is best beyond just the predictive accuracy. Model ensembles tend to typically be the most accurate, but often will fare worse along these other dimensions. Recall that we can use autoglon to make predictions with any of the trained models. Here, let's predict on the first 20 data points in the test data using this light GBM model from the first stacker, the base stacker layer. So L0 here refers to a base model, meaning it operates directly on the original data points, the original data features, I should say. This is actually a bagged ensemble of 10 different light GBM models, recall. Here shown here. And so that means that model will actually take 10 times as long as a single light GBM model to produce predictions, and it may require 10 times the memory. Instead, we can collapse this bag of 10 light GBM models into just a single one that's refit to the full data set. Here, the refit model will early stop at the average of the 10 early stopping points previously used in each one of the bagged light GBM models. So each one of those models had a different validation set and a different training set, so they each early stopped at different points that were optimal for their respective validation sets. Here we call refit full on this model specifically, and it will return the original name of the model. This is the bagged ensemble here, and the refit version of this model, which in this case is just a single model now. And yet, as I said before, this model will just require 10x less memory and 10x, it'll be able to produce predictions 10x faster if the bagged ensemble is not parallelized. Here we show the process of using this refit full single model For prediction, again, the first 20 data points, and we can print out its information. Here we see that it has no children models because, again, it's just a single model, not a bagged ensemble. While computationally favorable, single individual models will usually have lower accuracy than weighted, stacked, or bagged ensembles. Model distillation offers one way to try and retain the computational benefits of a single model while enjoying some of the accuracy boost that comes from ensembling. The idea is to train the individual model, which we now call the student, to mimic the predictions of the full stack ensemble, which we call the teacher. Rather than fitting the individual model to the training data target values, one can fit this student model to an alternative data set whose target values are predictions from the teacher. In classification tasks, the teacher provides its predicted class probabilities as targets for the student to predict, which may encode richer information about the class similarities or label noise in the data. We can also blend the teacher predictions with the original target values from the training data for further improvement. Distillation in autoglon follows the strategy proposed in this paper, which we call augmented distillation and display below. The overall augmented distillation procedure involves 4 steps. First, we fit the stack ensemble model to the original training data, both its features and labels. Next, we use the training data features to somehow generate a synthetic data sets of fake feature values, which we call the augmented data. The augmented data should ideally follow a similar underlying feature distribution as the training data, and they can be either generated, say, via simple feature permutations or perturbations of values in the training data, or via some generative model trained on the training data features that learns to generate new values that follow the same distribution. Next, we use the stack ensemble model to make predictions on the features in the augmented data set. This produces labels for the augmented data, aka target values that our student should learn to mimic. In classification, these will be predicted class probabilities rather than predicted class labels. Finally, we merge this augmented data set of features and labels together with the training data set of features and labels and train the student model on the entire enlarged data set just in the usual fashion. In this second step, where we're generating augmented data, we typically will generate 5 to 10 times as many augmented data points as there are training samples. This way, the student model can better mimic the teacher by being trained to replicate its predictions at a vast number of points in the feature space. In autoglon, we can show how to perform augmented distillation using a light GBM student model, say. Here we call predictor.distill on our previously trained stack ensemble predictor. And here we specify GBM in hyperparameters, which means, again, autoglon will only train a light GBM model. Here we've increased the verbosity a bit to see some more output. Here we see that it's distilling with 4,000 synthetic data points. This model now begins training to mimic the ensemble predictions over these synthetic data points. And finally, it completes training and produces some validation score. We can use this distilled model for prediction and compare its accuracy with all the models previously trained during FIT. Here we use it for prediction, where the student name was returned by the distillation function previously. And we can also call leaderboard. Now this distilled model will be included in the predictor object. So here, in this case, the distilled model has the suffix distill shown here. This is its accuracy. Here we just use the default hyperparameters that autoglon would normally use for its light GBM models, but we could also specify much smaller hyperparameter values if we want to get more lightweight models as students. Now we're going to shift gears slightly and study feature importance. Often, high accuracy on some test data may not be enough for us to really trust that our trained predictor will lead to the right decisions when deployed. We might also want to understand which features the predictor relies on to make accurate predictions. It's not uncommon that a dataset contains spurious correlations due to how it was collected, or it has some sampling bias. For example, radiologists in 2017 discovered one accurate ML classifier based on X-ray images was basing its cancer diagnoses on the spurious presence of a ruler in these tumor images because dermatologists who were concerned about tumors tended to include a ruler in their imaging. One way to quantify how much each feature individually contributes to an already trained predictor's accuracy is via a method called permutation shuffling. Here we randomly permute one column's values corresponding to the measurements of one feature across the rows of the dataset and measure the resulting drop in predictive performance when the predictor is asked to predict on this resulting data. The size of this drop can be considered the feature's importance score, basically how much predictive signal did this feature provide, because once its values are shuffled, all of this predictive signal is basically destroyed. This way of scoring feature importance is often more trustworthy than many alternatives that make a lot of approximations or are based on often unrealistic assumptions. For our trained autoglon predictor, we can compute feature importance scores like this. We have the feature importance function. Here we call it on the test data, so we will be measuring the drop in predictive performance on the held out test data when each feature in the test data is permuted across its rows. Here we show the performances that result, and here you can see some of the top features with the most importance include the primary diagnosis. Recall that our task here is to predict hospital readmission within 30 days, over 30 days, or no readmission on record. So here we see that the most important features for predicting this include the primary diagnosis of the patient, the medical specialty to which, what kind of doctor they're referred to in the hospital, the previous number of inpatient visits that this patient had, their secondary diagnosis, the number of procedures they had during this hospital stay, the number of medications they were on during this hospital stay, etc. And so these all seem like pretty reasonable features that you would expect would help you predict whether or not a patient will need to be readmitted in the near future. If reducing inference latency matters to us, this is still a useful method because we can now retrain a much more efficient predictor that only operates on a subset of the most useful features. For example, here we only keep those features whose importance in the previous result was positive. Other features basically showed either no drop in predictive performance or even possibly a negative drop in predictive performance, meaning the accuracy of the resulting predictor actually improved when they were shuffled, probably just due to random chance. But features that have non-positive feature importance scores presumably are not providing much predictive signal anyway, and so we might as well just get rid of them. So here we get rid of these features, so we only have a small feature subset. We now create a smaller training data set with only the columns in this feature subset shown here. It's much smaller. As you can see, I think our previous full diabetes data set had something like 40-something columns. And then we can train a predictor on just this reduced subset. And then call leaderboard on the resulting predictor. And you can still see some models are able to do pretty well on a test data set now that only has the subset of features as well. But more importantly, the prediction time has gone down a great deal because both the models end up being smaller when they're trained with less features, and just the amount of computation you need to do to process data with less features is significantly reduced. Next, we're just going to talk about how you should actually use autoglon for ML deployment if you choose to pursue this in your own applications. Here we're focusing primarily on applications where inference latency or costs matter. For example, these are often settings where you're making predictions one data point at a time. For these types of settings, here's how we recommend you train autoglon. we recommend you use the presets argument here that can allow you to describe some qualitative things that matter to you in the resulting predictor. For example, here we specify the good quality, faster inference preset that says we kind of care about getting pretty good accuracy, but we really want to have fast inference. The only refit means that we will refit all our models, all our bagged models, and collapse them into single models. Recall that that can lead to a massive speed up and reduction in memory requirements. Finally, we also specify another preset, optimized for deployment. This deletes any additional files that are not needed in the final predictor. For example, other models autoglon might have trained that are no longer being used, and other auxiliary training files that you just no longer need, so that the resulting file that contains the predictor object is as small as possible and you can deploy it on some limited hardware. If you require even lower latency, we recommend you additionally specify the following fit argument. The hyperparameters argument can not only take a dictionary of hyperparameters, but it can also take some qualitative strings that just say, I would like light models or very light models, where the very light models will be extremely small, the light models will be fairly small, at least smaller than the default hyperparameter settings. And additionally, we encourage you try using distill and hyperparameter tuning, where you might specify a search space over just hyperparameter configurations that you know are pretty efficient. Here's how we can deploy the trained predictor now on a new server. We can load the model from the folder that we previously provided to fit. Again, it's unnecessary here because we're still in the same Python session, but this would be needed if you were in a new Python session. Then we call persist trainer. This makes sure all models are loaded into memory so that autoglon doesn't need to load anything from disk when it is given a data point to predict on. Here we can see what the resulting predictor looks like via the getInfo function or the info function. And here you can see the models that it contains and that it requires to produce predictions. Now we go ahead and produce predictions on one data point at a time. Obviously, this is not how you should be doing it if you have the full test data set available, but we're just trying to show what it might look like in a real application. Here's just one patient's data, for example, and then we can produce one prediction for such a patient. Finally, we can evaluate the resulting accuracy of these predictions just as before, along with other performance metrics, which are important always to evaluate when you're considering which model to deploy. We encourage you to check out these references if you want to learn more. This concludes the portion of our tutorial focused on tabular data. In the next portions of the tutorial, we'll concentrate on image and text data and more around deep learning models.